If the entire history of the universe were compressed into a single year, the first second would occupy a fraction so small it would disappear into abstraction. And yet, within that sliver of time, the fundamental architecture of reality settled into the form we now recognize. The early universe was not a place in the conventional sense. It was an evolving state of space-time at energies far beyond those accessible in any terrestrial experiment. Temperature was not merely high. It was so extreme that distinctions between familiar particles dissolved into a seething equilibrium of fields and excitations. In those earliest instants, what we call forces today may not have been separate at all. The electromagnetic and weak interactions are known to unify at sufficiently high energies into the electroweak force. At even higher scales, some theories suggest that the strong interaction merges with them, hinting at a grand unified framework. Whether such unification truly occurred remains experimentally unverified. But the mathematical structure of particle physics strongly implies that symmetries present at high energies fractured as the universe cooled. Cooling is central to the story. Expansion stretches spacetime, and as spacetime expands, radiation redshifts. The average energy per particle decreases. Temperature falls not because heat escapes into a surrounding void, but because space itself dilutes energy density. As the temperature descended through critical thresholds, symmetry-breaking phase transitions likely occurred. The Higgs field, which permeates all space, settled into a non-zero value. Particles that had once behaved as effectively massless acquired mass through interaction with this field. The transition did not resemble ice forming in water, yet the analogy is useful. A uniform high-energy state gave way to a lower-energy configuration with distinct properties. The acquisition of mass-altered reaction rates and interaction strengths. It reshaped the behavior of matter at a fundamental level. Meanwhile, the universe was still in thermal equilibrium. Particle species were created and annihilated continuously. For every quark, there was an antiquark. For every electron, a positron. Energy transformed freely into particle pairs so long as temperature remained high enough. Then, a subtle imbalance emerged. The mechanism behind this imbalance remains one of modern physics' most compelling puzzles. The observable universe contains far more matter than antimatter. Yet the laws governing particle interactions appear almost symmetric between the two. Certain processes violate charge parity symmetry, meaning that matter and antimatter do not behave in exactly mirror image fashion. These violations have been observed in laboratory experiments involving mesons. However, the degree of asymmetry measured so far seems insufficient to account fully for the cosmic imbalance. Still, during the first second, conditions were extreme enough for baryon number violating processes to occur in certain theoretical models. If those processes took place while the universe was departing from equilibrium, such as during a phase transition, they could generate a slight excess of baryons over antibaryons. That excess was tiny, roughly 1 extra baryon per billion particle-antiparticle pairs. Yet that minute difference determined the fate of the cosmos. As expansion continued and temperature dropped below the threshold for pair production, annihilation dominated. Matter and antimatter destroyed one another in vast numbers, converting mass into radiation. But because of the asymmetry, a small residue of baryons remained. All later structure formed from that residue. Within microseconds of the beginning, quarks became confined inside hadrons. This transition occurred when the temperature fell to a level where the strong force's peculiar property, confinement, became dominant. Free quarks, once part of a quark-gluon plasma, could no longer roam independently. They combined into protons and neutrons. The universe, at this stage, consisted primarily of photons, neutrinos, electrons, positrons, protons, neutrons, and dark matter particles whose identity remains unknown. Neutrinos, interacting only weakly, soon decoupled. Their interactions with other particles became too infrequent to maintain equilibrium as expansion accelerated. From that moment onward, they streamed freely through spacetime, forming a background analogous to the later cosmic microwave background, though far more elusive. The first second was not dramatic in a cinematic sense. There were no explosions visible to observers. There was only cooling, symmetry breaking, annihilation, and decoupling, all governed by precise quantum field equations operating under rapidly changing conditions. And yet, everything depended on the exact timing of these transitions. Had the expansion rate been slightly different, equilibrium might have persisted longer, altering particle abundances. Had the asymmetry between matter and antimatter been absent, the universe would contain no atoms. Had neutrinos coupled more strongly, the thermal history would have shifted in measurable ways. The first second fixed the composition of the universe in broad outline. The subsequent billions of years merely elaborated upon that outline. Take a slow breath. In that fleeting interval, the fundamental constants were already in place. The strengths of forces, the masses of particles, the structure of quantum fields, all operating according to laws that remain consistent today. The early universe was not unstable chaos. It was an arena where extreme energy revealed underlying symmetry and then gently fractured it. From near perfect balance, a slight imbalance endured. From uniform plasma, differentiation began. From abstract quantum fields, the material content of the universe emerged. In the next movement, we will examine how the freeze-out of interactions shaped relic abundances, how neutron decay influenced nuclear outcomes, and how the first minute set the stage for the formation of light elements. The first second established the rules. The next few minutes began writing the first enduring matter into existence. As the universe expanded past the first second, its temperature slipped below the threshold at which weak interactions could maintain equilibrium between protons and neutrons. Earlier, these two particles transformed into one another through reactions mediated by the weak force. Electrons and neutrinos participated in processes that constantly reshuffled the identity of nucleons. The ratio between neutrons and protons was therefore governed by thermal equilibrium, determined primarily by their mass difference and the ambient temperature. But equilibrium requires time, and time, in an expanding universe, is constrained by expansion itself. When the reaction rate of weak interactions fell below the rate at which spacetime stretched, the balance froze. From that moment forward, the neutron-to-proton ratio no longer tracked temperature precisely. It was locked in, slightly favoring protons because neutrons are marginally heavier. That difference in mass, small as it is, shaped cosmic chemistry. Neutrons are unstable when isolated. Outside atomic nuclei, they decay with a mean lifetime of about 15 minutes, transforming into protons while emitting an electron and an antineutrino. In the early universe, after weak interactions froze out but before nuclei formed, free neutrons began to decay. This decay further reduced their abundance. Had the neutron lifetime been significantly shorter, far fewer neutrons would have survived long enough to bind into helium. Had it been much longer, the helium fraction would have been greater. The balance was delicate. For several minutes, the universe remained too hot for deuterium, the simplest bound state of a proton and neutron, to survive. Even if a proton and neutron fused, energetic photons immediately tore them apart. The photon bath still contained too many high-energy quanta capable of photodissociation. This bottleneck delayed nucleosynthesis. Only when temperature dropped below roughly 0.1 megaelectron volts did deuterium become stable against immediate destruction. Once that threshold was crossed, nuclear reactions proceeded rapidly. Protons and neutrons fused into deuterium. Deuterium combined into helium-3 and helium-4. Trace amounts of lithium formed through less efficient channels. The window for these reactions was brief. As expansion continued, density fell. Nuclear collisions became too infrequent to sustain fusion. Within about 20 minutes of cosmic time, nucleosynthesis effectively ended. The result was not arbitrary. Roughly 3/4 of baryonic mass remained as hydrogen nuclei. About 1/4 formed helium-4. Only tiny fractions became deuterium, helium-3, and lithium. These proportions are not inferred from theory alone. They are measured in ancient gas clouds whose chemical composition reflects primordial abundances. The agreement between observation and calculation stands as one of the strongest confirmations of the hot Big Bang framework. What is striking is how much depended on subtle physical parameters. The expansion rate during nucleosynthesis depends on total energy density, including contributions from neutrinos and any additional relativistic species. Observations of light element abundances therefore constrain the number of effective neutrino families. The measured value aligns with predictions from particle physics. Thus, cosmology and high-energy physics intersect within the first few minutes of existence. Dark matter, though not participating in nuclear reactions, influenced expansion indirectly through its contribution to energy density. Its presence subtly altered the timing of events. After nucleosynthesis concluded, the universe consisted primarily of hydrogen nuclei, helium nuclei, electrons, photons, neutrinos, and dark matter. No heavier elements existed. Carbon, oxygen, iron, everything essential to planets and biology, would require stellar furnaces much later. At this stage, matter and radiation remained tightly coupled. Photons scattered frequently off electrons, maintaining thermal equilibrium. The plasma glowed intensely, though no observer existed to see it. The first second had established particle abundances. The next few minutes had fixed elemental ratios. From then onward, the universe entered a long period of gradual cooling and expansion, during which gravity quietly amplified slight density variations. Take a slow breath. The early cosmos was governed by quantum field theory under extreme conditions. Yet its outcomes are written into the chemistry of intergalactic gas today. The proportion of helium in distant galaxies echoes decisions made when the universe was minutes old. The existence of hydrogen, the simplest atom and the most abundant element, reflects a competition between decay rates and expansion. Nothing in those first minutes was decorative. It was foundational. In the next movement, we will examine how radiation dominated the early universe, how fluctuations evolved within the plasma, and how the first second continued to influence structure long after nuclear reactions had ceased. The first second did not vanish into the past. It persists in every atom around us. Once nucleosynthesis concluded and the first minutes passed, the universe did not enter stillness. It entered a prolonged era in which radiation governed its dynamics. Energy density in the early cosmos was dominated not by matter, but by photons and relativistic particles. In such a radiation-dominated epoch, expansion behaves differently from the matter-dominated phase that would follow much later. The scale factor grows more slowly with time, and density falls rapidly as both dilution and redshift drain energy from the radiation field. Matter existed, but it was dynamically subdominant. This distinction matters because the growth of structure depends on which component dominates gravitational dynamics. In a radiation-dominated universe, density perturbations in ordinary matter cannot grow efficiently. Radiation pressure resists compression, smoothing fluctuations that attempt to deepen. Yet not all matter interacted with radiation in the same way. Dark matter, if composed of non-relativistic particles that interact only weakly with radiation, was already beginning to cluster gravitationally. Unlike baryonic matter, it did not experience photon pressure. It responded only to gravity. Thus, while the visible plasma oscillated under the competing influence of gravity and radiation pressure, dark matter fluctuations quietly deepened. This early divergence would later become decisive. The density perturbations themselves originated much earlier, possibly during inflation. Inflation provides a mechanism by which quantum fluctuations in scalar fields become stretched beyond the causal horizon. Once stretched, they become classicalized perturbations imprinted in space-time curvature. After inflation ends and standard expansion resumes, these perturbations re-enter the horizon at later times as slight overdensities and underdensities. Their amplitude was extraordinarily small, about 1 part in 100,000. Yet gravity does not require dramatic imbalance. Given enough time, even minute excess mass attracts additional matter. Growth begins subtly and accelerates gradually once matter dominates expansion. The first second, therefore, determined not only particle abundances, but also the statistical properties of fluctuations. The spectrum of perturbations, their distribution across scales, reflects conditions in the earliest moments. Observations of the cosmic microwave background confirm that this spectrum is nearly scale invariant, as predicted by simple inflationary models. In other words, the seeds of galaxies were planted when the universe was younger than a heartbeat. As radiation continued to dominate, the universe remained opaque. Photons scattered frequently, maintaining thermal equilibrium. The plasma supported acoustic oscillations, compressions, and rarefactions that traveled outward from overdense regions. These oscillations carried information. The characteristic scales set by the sound horizon at that epoch remain imprinted in both the microwave background and the large-scale distribution of galaxies. Even billions of years later, astronomers can detect the preferred separation scale corresponding to these early oscillations. The physics of the first second echoes across cosmic time. Eventually, as expansion diluted radiation energy density more rapidly than matter density, a transition occurred. Matter began to dominate gravitational dynamics. Only then could density perturbations grow efficiently into the nonlinear structures that would become galaxies and clusters. But that era lay hundreds of thousands of years ahead. In the first second and its immediate aftermath, the universe established a template: the abundance of baryons, the relative fraction of radiation, the presence of neutrinos, the existence of dark matter, and the statistical imprint of quantum fluctuations. These were not surface details. They were initial conditions for everything that followed. Consider how fragile this architecture was. A slight change in the strength of the weak force would alter neutron freeze-out timing. A different expansion rate would shift helium abundance. An absence of dark matter would prevent early clustering. A different fluctuation spectrum would produce a universe either too smooth for galaxies or too chaotic for stable structures. The first second was not merely an origin in time. It was a calibration of physical law under extreme conditions. Take a slow breath. The atoms around you were shaped by decisions made when space-time itself was barely unfolding. The ratio of hydrogen to helium, the existence of background neutrinos, the amplitude of primordial fluctuations. These are not incidental. They are relics. The early universe has left signatures everywhere: in nuclear abundances, in cosmic background radiation, in the distribution of galaxies, in the very possibility of chemistry. When we speak of the first second, We are not referring to a distant curiosity. We are describing the moment when the universe settled into the parameters that would allow complexity to emerge. From that fleeting interval came the long unfolding of cosmic history. The first second ended. Its consequences did not.